Hello, everybody. We are in chapter 25, and this is human interactions with the biosphere. All right. If you take a look at the human population, you just go back a couple hundred years, you can see what's going on with the human population growth. You can probably already look at this graph and tell what kind of growth curve this is, but we are exponentially growing. So, year 2026, we're at over 8 billion people on the planet. And you can see that this world population really began to accelerate. It was around 1920 we began to accelerate. So while there's been advancements in medicine and sanitation and all the things, essentially what we're seeing is that we are able to support a bigger and bigger and bigger human population. But everyone asks, when will it stop? Where's the carrying capacity? At what point in time have we tipped the Earth's ability to feed this huge planet to an unsustainable situation? So biotic potential is the maximum growth rate under ideal conditions. So we've had a lot of biotic potential with our advances in understanding of chemistry and botany and soil. We have been able to grow more and more and more food. What agriculturalists tell us is that we're using the best land that we have to grow food. So just to say, oh, well, let's just grow food over there and over there and over there and over there, is not necessarily a sustainable solution to our food issue. Our food issue needs to drill down into some alternative farming practices. But nevertheless, biotic potential is essentially the maximum growth rate under ideal conditions. Now, limiting factors are going to decrease the population's ability to grow at this maximum growth rate. Instead, it's going to curb or slow down or limit the ability for the population to grow. So not enough food is a limiting factor. Having plenty of food is biotic potential. Okay, so it goes both ways. So there's lots of situations that can essentially prohibit a population growing. Disease, war, famine, it goes on and on and on. Okay? So again, when we think about this idea of carrying capacity, it makes us wonder, how many people can the planet support? So there's a large variation of what those people who do these kind of calculations think. So they think the Earth can handle 50 to 100 billion people. Can you imagine? What does that look like? We're at 8 billion people already. So let's look at more developed countries, or MDCs, versus less developed countries, or LDCs. So our more developed countries, these are what we used to call our first world countries. That's not a word that we use anymore. We just say more developed, less developed. So we are more developed. So North America, Europe, parts of Asia, of course, more developed. So our growth rate is modest. Like, there's definitely, birth control. There's definitely opportunities for women to get out in the workforce. And so when we see increased opportunities for women, then we see that the birth rates are lower and more sustainable. So the growth rate is more modest. We also see that there's a higher standard of living. In our less developed countries, so some countries in Asia and Africa and Latin America, we know that population growth rate is dramatic. And the majority of the people are not living in a high standard of living. Instead, they're living in poverty. So there's a few things going on there. But essentially, not having access to all of the technology and advances that we have in a more developed country is going to limit less developed countries to an earlier stage of what we call the demographic transition. Okay, so we can take a look at our more developed countries. And between 1850 and 1950, we doubled our populations due to, yes, modern medicine, right? So people were living longer. Also, we could see that birth control came into the picture at the latter part of those years, and that allowed women to control their fertility, so they had fewer children. In addition, we received improved socioeconomic conditions. There were more jobs. There was a lot of money to be made. Now, things are really different looking at 2026 than 1950. But we saw there was a decline in death rate, and usually in what I referred to, I don't think we'll ever come across it in this chapter, is a demographic transition. But essentially, when you're looking at the advancement of a country or the development of a country, we see that death rate drops first, and then there's a decline in birth rate. So we see that our more developed countries experienced only modest growth since 1950. And in fact, that's about 0.1%, a tenth of a percent. Now, in contrast to other more developed countries, growth rate in the United States has not leveled off. So we are still growing, but we're noticing in the past year or so that birth rates are decreasing. So we're at about 333 million people on the planet. And we do have some population growth due to immigration. Okay, so what's the story in a less developed country? So we see that death rate is really high. So while it declined steeply following World War II, and that was really due to the development of modern medicine, the birth rate remained high. And again, that's because these countries are really stuck in a situation where they're not advancing so that there's equal rights and that there's the flourishing of opportunities, which usually comes along with jobs. Where do you get jobs if you're in sub-Saharan Africa? So the growth rate of our less developed countries peaked at about 2.5% between 1960 and 65, and they are declining, but still very high. Okay, so some more stuff, but let's just move on. These age structure diagrams are interesting because it gives you a snapshot of what's going on in a population of a country. So look what we have here. We've got on the y-axis cohorts of individuals. So essentially your 0 to 4-year-olds, 5 to 9-year-olds, 10 to 14, and so on. And then you have this band, right? So you got this little band across that represents the number of individuals in that cohort or that age group. So here between 0 and 19, they're labeling that pre-reproductive. And what you're going to see here is on the right-hand side of the graph, the bar represents the number of females in this pre-reproductive stage, and on the left-hand side, the number of males. Now, when we get to the 20-year-old mark, we call this the reproductive age up to 45. Again, the right-hand side, the females, left-hand side, the males, and so it goes. And the very last group here is the post-reproductive. So you get an idea of how many males and females are in each cohort for each of these kinds of life stages, if you will. So if we're taking a look at post-reproductive individuals, these individuals aren't contributing to the population growth because they are non-fertile, right? Or post-reproductive. These are the individuals we have to but think about how many children are they going to have during their lifespan of their during the reproductive age, okay? And we can also see like if there's some disparities. So slightly more male babies are born than female babies. And then up here we see that women live longer than men. So there's a lot of really interesting things you can ascertain from these figures. Now notice, look how different this slide is. So this is representing the less developed country. Take a look at the huge broad base. Now we should compare apples to apples, so we're looking at like 275 million males and just under that for females. And we come over here and we're looking at, oh, look, maybe about 80 million males and maybe about 75 million females. So yeah, there's a very vast difference in birth rates between more developed and less developed countries. Again, we see the same idea, males on the left, females on the right. And what you see how this just looks like steps? This is showing us that, hey, if you're born in this cohort, if you just kind of look to see who was born, 45 years ago, take a look at how many deaths likely occurred, right? We don't really know without looking back at the exact same thing like this, but 50 years ago. But generally speaking, when you see these steep sides of this pyramid or this triangle, that's telling you there's a high death rate. See here? Now, what this is showing us in this country is that there's slight negative population growth. So 50 years ago, more babies are being born. Now, less babies are being born. Okay, let's move on to our resources. So non-renewable resources are in limited supply or can be exhausted or would take so long to replenish that essentially it's non-renewable. So land, fossil fuels, minerals. Renewable resources can either be renewed on a daily basis, like we're thinking about the sun, plants regrowing, or it may be a little bit more drawn out. So maybe water percolation into the soil post a drought, and then it going into the aquifers. That might take a little bit longer, but yes, it is renewed or replenished. It just might take a little bit longer, whereas sunlight is on demand all the time, except for at night, of course. All right, biodiversity, another topic in this chapter, the variety of life on the planet. So there's been lots of attempts to, estimate how many different kinds of life are on the planet. So there's the low amount of, we've named about 2 million species, but there's so many out there that we know that we don't know because we can do some modeling and do some sampling and see how many we don't know. So there's been speculations that there's 10 million, 50 million up species on the planet. The trouble is that we don't really know because there's a lot of Earth that humans have not even set their foot on. We're presently in a biodiversity crisis. So the number of extinctions currently is far greater than what you would expect to be what we call natural or background extinction. Background extinction is 1 to 2 species per million species that are on the planet per year. So now they tell us that number is 10 to 100 times, 100 to 1,000 times higher. So if it's 1 to 2 per million, then now we're looking at 100 to 200 up to 2,000 species are going extinct per million per year. So 1 to 2 compared to 100 to 1,000 is a vast increase. We have our current causes for loss of biodiversity. I'm going to hit HIPO, that's habitat loss, invasive or non-native species, pollution and over-exploitation or over-consumption. There's another P, human population, and then there's C, climate change. So I like to think about it as HIPPOC. I'm not going to address disease. I am going to slowly go through these slides so you can take notes. Pause if you need to. But habitat loss is kind of a no-brainer. We're wiping out tropical rainforests, coral reefs, wetlands, and now you've displaced organisms. And if they are specialized to a niche that's only in that particular ecosystem or biome, then they are going to struggle to survive. Invasive species are those that don't belong here naturally, but they've moved with us as humans move around. So through colonization, horticulture. So, if someone's like, oh, I saw this really exquisite lady slipper orchid, and then they dig it up and bring it home, then certainly we're doing it because we love the beauty of it. Maybe we want to breed it. But by doing so, we're, essentially moving it to another place where it doesn't belong. There's been a lot of accidental transport, of course. So we've had the zebra mussel move around in the ballast water of ships for a number of decades, and that was accidentally, but now we know, to look for that and test for that. Pollution. So pollution, in whatever form that is, usually we have organic chemicals released into the environment that don't belong there, so it can, weaken, like thinking about acid rain, weakens trees. And it actually increases their susceptibility to disease and insect infestation. We know that agricultural runoff can lead to what we call dead zones. So that's a serious situation where we're losing fish life in our oceans. And then we also know that organic chemicals in the water can disrupt hormones. So we have endocrine disruptors. See you in part 2.